The WKB approximation 2. The WKB approximation can be used to calculate the energy levels for a harmonic oscillator. In this approximation, the energy levels are the solutions to the equation given here, where E is the energy and position-dependent potential energy function is U of x, and x equals A and x equals B are the classical turning points, the points at which the total energy is equal to the potential energy, so the Newtonian kinetic energy would be 0. Part A, determine the classical turning points for a harmonic oscillator with energy E and force constant K prime. For a harmonic oscillator, we have no non-conservative forces, therefore the kinetic energy K plus the position-dependent potential energy is equal to 1 over 2 mv squared mass times velocity squared plus 1 over 2 force constant K prime x squared, and that's equal to the total energy E of the harmonic oscillator. Now, when we have K is equal to 0, the potential energy term, which is 1 over 2 K prime x squared, becomes the total energy E. Therefore, we find that the value of x that corresponds to the classical turning points is plus or minus 2e over k prime inside the square root. So these are the turning points. That's our answer to part A of the problem. Let's move on to part B. Carry out the integral in the WKB approximation and show that the energy levels in this approximation are an h bar omega, where omega is square root k prime over m and n is 1, 2, 3, etc. Hint, recall that h bar is h over 2 pi. A useful standard integral is the integral of square root of a square minus x squared dx, which is 1/2 square brackets x square root a square minus x square plus a square arc sine x over absolute value of a. Note that the integrand is even, so the integral from minus x to plus x is twice the integral from 0 to plus x. Okay, now we're using the WKB formula, integral between the turning points A and B, 2m square brackets E minus position-dependent potential energy, all inside the square root, dx. This must be equal to n times h Planck's constant divided by 2. This is known as our WKB approximation, where the turning points are the ones that we have calculated in part A of this problem. A is minus square root of 2e over k prime, and the other turning point, B, is plus square root 2e over k prime. Okay, now we're going to apply this. So if I write the integral from a to b, 2m, I'm substituting for the potential energy 1/2 k prime x squared. This is all inside the square root dx. This is equal to, if I multiply this by 2, it will be 2e minus k prime x squared divided by 2, and these 2's will disappear. So I will obtain integral from a to b 2e minus k prime x squared inside the square root dx, because this 2e divided by 2 will get rid of this 2, and then I will take square root of m. I note that there's a square root of m here. There is my square root of, not 2m because 2's disappeared, square root of m outside. And now I'm going to take this into also k prime parentheses. So I will have square root of mk prime up front, integral from a to b 2e divided by k prime minus x squared. This is inside the square root dx. All right. And let's do this. Let's call a squared equals 2e over k prime. With that, this integral, so let's keep this in mind. This integral is going to become square root of mk prime integral from a to b square root of a squared minus x squared dx. And we are given the answer for this integral. It was given as a hint. This is the answer. So let's substitute that here. This will tell us we have square root of mk prime 1 over 2 x times square root of a squared minus x squared plus a squared sine inverse arc sine x divided by absolute value of a. This is the answer to the integral. But now I notice that this function f of x equals a squared minus x squared to the power 1/2 is an even function. So due to its symmetry, instead of taking these limits between a and b here, I can take it between 0 and b, which is 0 and square root 2e over k prime, and multiply it by 2 because I have the same thing for negative x values. So these 2's will cancel out. So here I have multiplied it by 2. And the 2's cancelled out. And now I substitute the endpoints. So I will have square root mk prime So if I substitute here square root 2e over k prime for x, 2e over k prime for x, and since a is also square root 2e over k prime, 2e over k prime minus 2e over k prime will give me 0, so this is 0, plus a square, which is 2e over k prime, arc sine x divided by a, since x is absolute value of a here, arc sine of 1. And then I will subtract from this x equals 0. X equals 0, arc sine 0 is 0, x is 0, so that doesn't give me anything. So this is all I have to calculate. And that gives me square root mk prime multiplied by 2e divided by k prime. And what is arc sine 1? It is pi over 2. Sine 90 is 1. So this is equal to nh over 2 according to WKB approximation. And you can see that these two 2's will cancel out. So I will be left with the following. The square root m over k prime 2 pi times energy E is equal to nh. So let's double check this here. I have square root k prime here and square root k prime square here. So this is square root m over k prime. And here's my 2 pi times E is equal to n times h. So from here I can get n from the energy to be n h divided by 2 pi is h bar square root k prime over m. This is my answer. And I note that this is in the form energy is equal to n h bar omega, where omega is square root k prime over m. So this is the final answer for the energy levels of the harmonic oscillator. Now, part C asks me, how do the approximate energy levels found in part B compare with the true energy levels, n plus 1/2 h bar omega? Does the WKB approximation give an underestimate or an overestimate of the energy levels? Okay. The energy levels are given by n plus 1/2 h bar omega. So WKB approximation misses the ground state energy E0 is equal to h bar omega over 2. Okay, so it underestimates. It underestimates and works well for the case where n is much greater than 1, so that this 1/2 will be negligible. So this is our conclusion after this analysis. Alright, so in this problem we have used the WKB approximation. First we started by looking at the classical turning points for the harmonic oscillator, whose total energy is E and force constant is K prime. So that's what we have found here by setting equal to kinetic energy term 0, and total energy equals potential energy. Then we have used the WKB approximation expression, and with the two turning points we have recognized in part A, and when we have solved this integral, we find that the energy levels are n h bar omega, where n is an integer, so n is integer 1, 2, 3, etc. But here we also have a solution for n equals 0, h bar omega over 2, and this solution is missed by the WKB approximation, so it underestimates the energy levels, but it will work well if n is much greater than 1, and this term will disappear, which is basically approaching the classical limit.